Hello everyone, welcome back to Liu Analysis. As part of the video, it is a continued discussion on comparison test. Comparison test, material-wise, I think it's pretty much like what we learned as undergraduates. And indeed, the first part of the statement, this is what I remembered as undergraduate. Usually, I write into this fashion for the series. Okay, first part of the comparison test. It's a sigma notation. Sorry, the writing does not look very pretty, but I still give it a try. But as simple as I can. Quick explanation for the first part of the comparison test, which is simply to say that if you are having a series which is less than a convergent series, Yn it is convergent, Yn it is convergent. And also note the absolute value notation there. Indeed, there are two reasons that we want to have the absolute value notation. First part of the absolute value notation, it guarantees all the terms are positive. Okay, it has floor there. It has a lower bound of 0. Okay, it cannot get to the negative part. And the second reason for the absolute notation, because we can make a stronger version of the convergence for the series. It converges absolutely, right? I say the series of xn converges. But anyway, because the absolute value notation, we can simply say it converges absolutely. So I remember, this is how I remember the first part of the comparison test as an undergraduate. And I hope it makes sense. It makes sense, right? Less than infinity. Well, even I say the less than infinity, but anyway, somewhat we really don't have to say anything something less than infinity, because that's the way how infinity it is. It is. Okay, nothing bigger than infinity. But we are really saying it is convergent. It is convergent. Okay. And the proof really follows directly from the Cauchy's criterion we mentioned in the early part. And the second part of the comparison test, well, we still can borrow notation infinity. Less than infinity means convergent. Greater than infinity means divergent. So the second part, we simply can say if we know the series in the fashion, well, put in this fashion, series xn, and I think this is might be better, even though statement may look different. Yeah, might do this way. Yn first, because we are going to say Yn is greater than xn, the series of x. Okay, but we do know the series of x, it is divergent. So when you have something bigger than a divergent series, and then we can say for sure it is divergent. It is divergent. Xn is given as divergent. I put a greater than there. Hope you see it doesn't make sense, right? We cannot have anything bigger than infinity. We really mean that's divergent. And then we have a series which is bigger than a divergent series. And then simply means the series must be divergent. That's a comparison test, pretty much the same thing like we did as an undergraduate. Okay, comparison test. And there are two simple examples I say. It should be easy to follow. By the way, it's worth to mention for this Liu analysis class, and mostly on the test, you may not see a problem as simple like that. Okay, we are going to ask you to write some proofs using the epsilon delta, or for the series, it is epsilon n language. Okay, to write some proofs. I would say some simple proofs, like I just like this is somewhat. And try to see if I can get I just saw there is a simple proof problem, proof of theorem written there. Yeah, there's something this kind of proof. Okay, so be prepared. You will be asked to write some proofs, and like for any epsilon positive, there exists uppercase n, which is certainly is integer, so that for n greater than n, and then you make you infer or you deduce the n equals to true, and then you make your conclusion. Okay, we will have proof questions, a lot of proof questions on the test. That's what I'm saying. For the lecture part, I don't think it will be very helpful if I read a lot of proofs to you. I'm just showing some simple examples. Okay, comparison test, and then what's the next part I have for my notes? I think one homework problem you may want to consider use this part of the theorem. And so for the moment, yeah, we have the proof. We have the proof. And again, I don't think if I read the proof right now to you, would it be very helpful? So I'm skipping the proof part. Okay. So what I really want to say, do consider the video as just a very brief summary of the content. Okay. And especially on the test, we may have proofs. I don't think this one's kind of complicated. We'll have somewhat of relative simple proofs on the test, okay, on the exam. That's all I can tell. Comparison test, and then the root test. It is still pretty much the same thing like what we learned as undergraduate, and I don't think there's anything unusual there, right? The root test, and I remember this is pretty much the same kind of thing we did as undergraduate. And then we have the ratio test, ratio test. It is still pretty much the same thing like we did as undergraduate, Okay. The ratio test, it tells the absolute convergence. Okay, absolute convergence. And there are 3 cases when such an alpha, it is strictly less than 1, the series converges absolutely. And then if not, if the alpha, it is greater than equal to 1, and then the series it diverges, ratio test. And also, oh, actually, yeah, after the ratio test and the comparison test, root test, this is really something I should have mentioned briefly, even though it's the same thing like we did in undergraduate. It's a power series, and also there is the concept of convergence radius or interval, the radius of convergence or interval of convergence, those kind of things. And the interval convergence, if you are using the ratio test, you can consider it's the reciprocal, the radius. It's the reciprocal of the ratio if you are using the ratio test. And usually, to consider the interval convergence, or the radius of convergence, you really need to use the ratio test. Okay. And this part of the lecture, it is about number E, Euler's number. At least I want to say you are going to know of 2, on this lecture part or on the textbook, there are 2 ways to calculate this number E, using the series expansion, and also using the limit, And indeed, they both converge to E. And also an interesting question, at least for now, I suppose we know there are 2 ways to calculate this E, and you may want to take a look. Or you want to do some actual calculation, which way is better. Okay, if you try, hopefully you should be able to tell which way is better to actually calculate the value of E there. Okay. Power series, and also in the end, we do have a conclusion. This shows from another aspect They're also the actual irrational numbers, not only the square root of 2. We started for this class, we started with square root of 2. And now we see it is also an irrational number. It is also an irrational number. And also on the textbook, there are some additional discussions on addition and multiplication between series. And especially there is a partial summation formula. I don't think I have the partial summation formula on the notes. One of the homework does require the partial summation formula. So you do use the book as a reference, okay, especially for the partial summation formula. And also in terms of series, and because series, simpler part, you can consider the sum of sequence, right? And you may want to consider the commutative property and the associative property for finite numbers. But you may want to know for series, which will make a difference. The commutative property and associative property cannot be applied to the sum or difference of a series, sum of series. Okay, they are simply different. So in the rearrangement part, I have another example about the alternating harmonic series. I hope you know alternating harmonic series really converges to log of 2. But somewhat I rearrange the term. At least you can take a quick look. All the terms, they all just from the harmonic alternating harmonic series. 1, 1/2, 1/4, 1/3. I did not even change the sign, but anyway, I did change the order of the terms, okay? Order of the terms. And so one possible rearrangement, if the commutative property is still true, we can write the alternating harmonic series in this fashion. And then through some work, you will see somewhat surprisingly, again, you want to keep in mind, the alternating harmonic series converted to log of 2. But if we change the order of the terms, make a new arrangement or a rearrangement of the terms of the alternating harmonic series, we possibly could get 1/2 times log of 2. And do keep in mind that this is not the only way. There are different ways. You may want to give a try. You may want to give a different try. Okay. So in general, I'm saying the commutative property, associative property cannot be applied to series, cannot be applied to series, okay, or cannot be applied to series. And also there's one exception. If we know the series converges absolutely, this is the last theorem on the textbook. If we know the series converges absolutely, and then basically every rearrangement of the series still converges. And they converge to the original sum, okay? Only in the case when you have a series converges absolutely, and then you can rearrange the terms of the series. Otherwise, you simply cannot. So I think this concludes the discussion on the topic of series. Thank you for watching. Let me know if you have any questions.